Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing into section 7.7, which was our introduction into numerical or approximate integration. In the previous video, we introduced or sort of reviewed a couple major ways of approximating definite integrals, the left endpoint, right endpoint, and midpoint approximation. And we introduced one new approximate integration technique, the trapezoidal rule, all of which are different ways of trying to estimate a definite integral without actually having to find the antiderivative. In this video, we're going to focus on two of those rules, the midpoint and trapezoidal rule, and talk a little bit about some formulas that help us understand the sort of size of the error that comes from trying to use these approximations. So these are what are called error-bound formulas, and what they try to do is they try to give us an upper bound or a maximum for what the absolute value of the error would be when performing one of these approximations. And what we mean by error, of course, is the difference between what the real value of the integral is and our approximation. So in other words, these are going to be formulas that sort of tell us how close our approximation is to what we actually, to what the real or true definite integral would be. So we're going to introduce these couple error-bound formulas and then look at a couple examples here. So we're going to suppose that we have a function f of x on some interval a to b, and we're going to further suppose that k, this constant k, is an upper bound on the absolute value of the second derivative of this function on that same interval. So in other words, k is the sort of maximum value that the absolute value of the second derivative can take on in that interval a to b. Then we get these following error-bound formulas, where E sub t is going to be our notation for the error for the trapezoidal rule, and E sub m is the notation for the error coming from the midpoint rule. So these formulas say that the absolute value of the error in the trapezoidal rule has to be less than or equal to k times b minus a cubed over 12n squared, and the absolute value of the error coming from the midpoint rule has to be less than or equal to k times b minus a cubed over 24n squared. So in a couple moments, we'll get into some examples of actually using these, but I want to investigate these formulas a little bit more. The first thing I want you guys to sort of notice from these formulas is that you have this b minus a in the numerator. What that basically tells you is that the larger the interval is, the more error you could potentially have. If you have a really large interval, the distance between a and b is very large, then b minus a is going to be large, and cubing it is going to make it even larger, meaning that the maximum error that might occur when you do one of these approximations is going to be larger. So, in other words, the larger the interval, the more potential there is for error. That should make sense. The larger the interval, that's a larger area that we're trying to estimate, which means we're going to have potentially more error. The other thing you should notice is that you have this n squared in the denominator. That means that as n increases, the maximum error is going to decrease, which should make sense, right? N is the number of partitions. It's how many approximations we're actually doing. So the more approximations you do, the more accurate your approximation is going to be. So that should also make sense. Now, the presence of this k, unfortunately, is a little bit beyond the scope of our class to investigate, but it should sort of make sense. K is an upper bound on the second derivative, the absolute value of the second derivative. If you think about what the second derivative is doing, it's measuring the concavity of the curve. In other words, it's measuring how fast the rate of change is changing. So the larger the second derivative is, the more quickly the curve is sort of changing slopes, which means it's harder to estimate because there's more rapid change. So that's why this k is sort of showing up in the numerator. The larger that k is, the harder it is to get a good estimate because the curve is changing very quickly. All right, so last thing I want to comment on this before we get into our examples is that these are error-bound formulas. You'll notice that this says that the error has to be less than or equal to these expressions, not equal to, meaning that the actual error might be significantly less than this. These formulas calculate the worst possible case for the error. The true error is just guaranteed to be less than or equal to that. So these are what we call these error-bound formulas as opposed to error formulas. There's no easy way to calculate the exact error unless you actually manually calculate the integral and compare your approximation to your integral. These are just simply formulas for the bound, the worst case scenario for the error. Okay, so let's go ahead and take a look at some examples here. So for our first example, we're going to consider this definite integral, the integral from 1 to 5 of 1 over x dx. Very simple one. This one we could actually just do manually. We should be able to come up with an antiderivative of 1 over x and plug in the bounds. But what I want to do with this is I want to determine the error bounds for the trapezoidal rule and midpoint rule with n equals 4, so a very small amount of partitions. Then we're going to write down and evaluate expressions for T4 and M4. So we're actually going to perform the approximations. Then we're going to directly evaluate this integral. Like I said, this is a very simple one, so we should be able to just directly evaluate it. And then in part D, we'll actually compare our evaluation in C to what we did in B, our approximations, and we'll actually see that the actual errors do fall within the error bounds. Now, this whole set of little problems associated with this is more to just make sure you really understand what does error mean, what is an error bound, and also just to review these approximations. In reality, in a real life situation, you wouldn't really do this because if you could directly evaluate this integral, why would you bother trying to come up with approximations? So this is more to just help you understand what the error bounds are, and then in the next example, we'll see one where actually evaluating it is impossible, so we have to use the approximations, and we'll use the error bounds to sort of determine how many approximations we would need to get a certain level of accuracy. But let's start with these here. So for part A, we want to determine the error bounds for the trapezoidal rule and the midpoint rule with n equals 4. So let's start with the trapezoidal rule. We know that the absolute value of the error in the trapezoidal rule is supposed to be less than k b minus a cubed over 12n squared. So before we can sort of plug into this formula, there's a couple things we need to know. We need to obviously know a and b and n and k. All right, those are the four things that we need to know to be able to plug in there. A and b are easy. Those are your ends of your interval. So a is 1 and b is 5. You also have n being equal to 4 here. So we know that we've got 4 there. And then this k, well, we're going to have to figure out what that k is because that's going to be based on the upper bound for the second derivative. So remember this here. K is upper bound on the absolute value of the second derivative on the interval 1 to 5. So we need to figure out that second derivative. So we have that f of x here is 1 over x. That means f prime is negative 1 over x squared. That's, of course, just treating this as x to the minus 1 and differentiating. And then the second derivative is going to be 2 over x cubed. And again, that's just treating this as negative x to the minus 2, dropping that minus 2 down and then subtracting by 1. All right, that tells us that the absolute value of the second derivative is also just 2 over x cubed on 1 to 5, because since we know x is between 1 and 5, then this x cubed is always positive, so the absolute value doesn't do anything here. And now we want an upper bound on this. Now, there is sort of a trick here. Technically, when you want to find a maximum of a function, what you need to do is you need to differentiate again, set that equal to 0, find the critical values, and then plug in those critical values and figure out what the maximum is. But actually, it's much easier here, and it's going to be much easier in most cases, because this is what we would call a monotonic function. This right here is monotonic. Monotonic means it has a single direction. In this case, this function is strictly decreasing. The larger x is, the smaller this expression is. So the larger the x is, the smaller the result of this. Remember, we want the largest possible value. So since it's going to get smaller as we plug in larger x's, we want to plug in the smallest possible x. Well, the smallest possible x on our interval is at x equals 1. So we're going to use x equals 1. So our k here is going to be equal to that absolute value of the f double prime at 1, which of course is going to just be 2 over 1 cubed, which is going to be 2. So we now know that our k is going to be equal to 2 here. So we can plug all this in and come up with our error bound for the trapezoidal rule. So the maximum error for the trapezoidal rule in absolute value is going to be 2 times 5 minus 1 to the third over 12 times 4 squared. And at this point, this is just something you could type into your calculator. So that's 2 times 4 cubed divided by 12 and then divided by 4 squared. So that looks like that's approximately 0.667. So we're saying that the maximum error, again, the real error might be less, but the worst case we could be is we could be off by 0.667 when we perform the trapezoidal rule with 4 partitions. Now, obviously, if we increase the number of partitions, if we did more approximations, this maximum error would shrink and we'd get a better estimate. Okay, let's go ahead and do this also for the midpoint rule because we wanted to do this for both of these rules. The midpoint rule should also be pretty easy. So the maximum error for the midpoint rule is kb minus a cubed over 24 times n squared. Then, again, we need to know a, we need to know b, we need to know n, and we need to know k. Well, again, a is 1, b is 5, n is still going to be 4, and this k, well, even though this is a different rule, the k is the same thing, right? When we stated these error bounds back here, we said that for both of these, this k references the upper bound on the absolute value of the second derivative on a to b. So in this case, we know that the k is just going to carry over as 2 here. So this means that the maximum error in absolute value for the midpoint rule is going to be 2 times 5 minus 1 cubed over 24 times 4 squared, which if we look at 2 times, again, 4 cubed, and then divided by 24, and then divided by 16, we should get that comes out as approximately 0.333. So you'll notice that the midpoint rule has actually got a lower maximum error, meaning that the midpoint rule cannot be as bad if it's in its worst case scenario as the trapezoidal rule. This doesn't guarantee that the midpoint rule is a better estimate because, again, this is the maximum error. We just know the worst case for the trapezoidal rule is worse than the worst case for the midpoint rule. But again, we don't know the actual errors based on this, just the maximum error. Okay, so that was using these new error bound formulas. Eventually, at the end of this sort of example, we'll actually see that the true errors are less than these error bounds. But to do that, we need to come up with some approximations. So let's continue on to a new page here. Now we're going to go ahead and write down expressions for and evaluate T4 and M4. So let's go ahead and do that. To actually do B here, we're going to have n equals 4. Which means that our delta x, the size of our partitions, is going to be 5 minus 1 divided by 4, which is going to be 1. So let's go ahead and draw ourselves a number line, starting at 1, sorry about that, and going to 5, and we're going to label by 1s, so they'll be 2, and then 3, and then 4. And when we go to do the trapezoidal rule, remember the trapezoidal rule is going to use every one of these. We're going to go ahead and take these individually, and then we're going to double the result of our approximation from each of these. So remember that T4 here is going to be delta x over 2, so it's going to be 1 over 2, times that f at 1 plus 2f of 2 plus 2f of 3 plus 2f of 4 plus f of 5 with f of x being equal to, well, the function that we're trying to perform the definite integral of, which is 1 over x. Now, this would be a totally fine way to write this. If we just needed to write down an expression for T4, this would be totally good because this says exactly what we're trying to do. It tells us what the function is and what we're plugging in and how we're sort of performing the approximation. But we do want to, in this case, go ahead and evaluate it. So we are going to go ahead and plug this in. So what we should get here is we get 1/2 times 1 plus 2 times 1/2 plus 2 times 1/3 plus 2 times 1/4 plus 1/5. And if we do that approximation, looks like we should get that this comes out as approximately 1.683. So there we go. It's 1.683 for our approximation there. Okay, so that's T4. Now let's go ahead and do the midpoint rule. So for M4, remember that for the midpoint rule, we're not going to use any of these. We're actually going to use the midpoints in each of these. So we'll be using this here, which would be 3/2, this here, which would be 5/2, this here, which would be 7/2, and this here, which would be 9/2. Remember, out front in the midpoint rule, you just put delta x. So in this case, we just have 1. We'd have 1 times f at 3/2 plus f at 5/2 plus f at 7 halves plus f at 9 halves, again with f of x being equal to this 1 over x function. Again, this would be a totally sufficient way if we just needed to write down but not evaluate the expression. In this case, though, we do want to come up with our actual approximation here. So this is going to be 2/3 plus 2/5 plus 2/7 plus 2/9. And if we put all that together, it looks like that should come out as 1.575 about. So there we go. There's our approximations, T4 and M4 in this situation here. Okay, now something that we can't normally do when we're doing approximations, but again, since I chose a very simple definite integral for us to try this on, we're going to directly evaluate this. So this is not something we would commonly do because, again, approximate integration is really used when you're unable to directly evaluate, but since we want to do a comparison, we are going to directly evaluate here. So we want to directly evaluate the integral from 1 to 5, 1 over x dx. That should be very easy because we know the antiderivative of 1 over x is ln absolute value x, evaluated from 1 to 5. So that's going to be ln of 5 minus ln of 1. And if we type that into a calculator to actually get a sort of decimal approximation, ln of 5 is about 1.609, and then ln of 1, of course, is 0. So we get that is 1.609. So there is our actual value, at least what the best a calculator can do with 3 decimal places. So, I mean, the true value is ln of 5, right? This right here, when we have it as ln of 5, that is the exact value of this thing. Of course, now it's an approximation because I'm writing a decimal for it. Okay, so let's actually now measure the true errors. So, if we're looking at the error for the trapezoidal rule, the error for the trapezoidal rule would be what our actual value is, which is at 1.609 minus the estimate from the trapezoidal rule, which is that 1.683. And we can see 1.609 minus 1.683. We can see that that comes in as being equal to negative 0.074, which means that the absolute value, in other words, the magnitude of the error here, is 0.074. So the trapezoidal estimate, when we did it with 4 partitions, was off by about 0.074. Is that within what we predicted? Well, the error bound said that the trapezoidal error was guaranteed to be less than 0.667. And you will notice that this is definitely way less than 0.667. So this is less than 0.667. Check. Of course, that's going to be true because those error bound formulas always work, but I wanted you guys to see at least one example where you actually confirm that the true error was indeed less than what we predicted from the maximum error bound. Let's go ahead and do the same for the true error for the midpoint rule. For the midpoint rule, the actual value was 1.609 minus what we found from the midpoint rule, which was 1.575. If we do that, we get that 1.609 minus 1.575. That error was 0.034. So you will notice that the midpoint rule in this case was a bit more accurate. And that tells us that the absolute value of the error here, of course, is just 0.034. Does this pass the error bound? Well, the error bound for the midpoint rule was supposed to be 0.333, so we're definitely under that, which of course we knew we had to be. So less than 0.333, sorry, less than or equal to technically. There we go. So what this shows us, at least in this very simple case, that these approximations that we do get, their true error certainly lies under that maximum error bound that is given to us by those formulas there. Okay, so this was more of an example to help you understand what we're trying to study when we talk about these error bounds. Our next example is going to be much more sort of realistic. We're going to look at a definite integral that we cannot directly evaluate, and instead of trying to do the approximations, we're going to try to figure out how many partitions, what value of n is necessary to guarantee a particular level of accuracy. So let's go ahead and look at that question. So we're going to consider this definite integral, the integral from 0 to 1 of e to the x squared dx. Now, e to the x squared is a very interesting function. It's pretty simple. It's just x squared plugged into the standard e to the x function. So it's a composition. It turns out, though, that the antiderivative of e to the x squared, at least as a closed form function, does not exist. So if you guys ever take a more advanced sort of calculus course, usually called like an analysis class, you can actually look into the proof that the antiderivative, the integral of e to the x squared dx, does not have a sort of closed form. And what we mean by a closed form is a single sort of functional expression that's equivalent as its antiderivative. Later on in this class, we'll learn a way of building a infinite series that is the antiderivative. That's not a closed form, though. It's going to be an open form using something called a Taylor series. But overall, actually trying to come up with an antiderivative of e to the x squared in a closed form is impossible. So this is exactly the type of thing where we probably, if we were given a definite integral that involved this function, would want to use approximate integration. So what we're going to do is we're going to determine what's the minimum number of partitions n necessary to estimate this integral to within 0.01. So we're saying to ourselves, we're okay if our answer is off by at most 0.01. And we want to figure out how many partitions would we need to divide this interval into to guarantee that the error is 0.01 or less. And of course, we're going to do the same thing using the midpoint rule. So let's go ahead and see how we would do this here. Now, of course, what's the whole point of this? Well, once you figured out what those minimum number of partitions would be, then if you were using like a software or something, you know, as long as you put more than that amount of partitions, you're guaranteed to have an error that's less than 0.01. So this is sort of preliminary work that you would use before you then use some software to actually go and run that approximation. All right, so let's go ahead and we're going to talk about our trapezoidal rule. So we know that the error in maximum for the trapezoidal rule is less than or equal to k b minus a cubed over 12n squared. And we want that to be less than 0.01. We want the error to make sure that we're within 0.01. So we're going to say that this needs to be less than 0.01. And we're really going to focus on this here. We're going to try to solve this thing. So we're going to take this. Okay, we're going to pull this over here. And we're going to say we're going to take k b minus a cubed over 12n squared less than 0.01, and our goal is to solve for n. How do we know that our goal is to solve for n? Because it says determine the minimum number of partitions n. So we know we're trying to find out n. So that means that in this expression, n is going to be the thing we're going to be solving for, so we need to know k, b, and a. So we need to know a, b, and k to proceed from here. So, of course, a and b are just the ends of the interval, which we have to have. So we know that a is going to be 0 and b is going to be 1. So that should be nice and easy. And then k, well, this is where we're going to need to look at that second derivative. So let's go ahead, and k is supposed to be an upper bound on the absolute value of the second derivative of this function on the interval 0 to 1. Notice it's not just an upper bound on the function, the absolute value of the second derivative everywhere. It's just on the interval we're working on. Okay, so our f of x here is e to the x squared. That means our derivative, we're going to have to use chain rule. We get e to the x squared, and then times the derivative of the inside, which is that x squared, so we get times 2x. So we have 2x e to the x squared. And then we're going to take our second derivative. Notice that we're going to have to apply product rule now. So the derivative of the first part is going to be 2, and then we keep the e to the x squared the same. So here for product rule, we're keeping this piece and this piece sort of separate. Then we're going to have plus the 2x, e to the x squared, and then chain rule again times 2x. So notice that gives us 2e to the x squared, plus it looks like 4x squared, e to the x squared. And if you wanted to, you could factor that as 2 plus 4x squared, e to the x squared. Now, it should be very clear that this is always going to be positive. So the absolute value of f double prime here is also just going to be 2 plus 4x squared, e to the x squared. And remember, what we want to try to do is we want to try to find the largest this can be on 0 to 1. Now, this part here is a quadratic, so as x increases, this is going to get larger and larger. And e to the x squared, well, we know that that's also an increasing function, so that's going to get larger and larger. So this, in this case, is strictly increasing, right? This just gets larger and larger as you plug in larger and larger values of x. So since we want it to be as large as possible, we want k to be an upper bound, and we're going to choose the upper end of the interval. So we're going to choose x equals 1. So that means k is actually going to be the second derivative, the absolute value of the second derivative at 1, which is going to be 2 plus 4 times 1 squared, e to the 1 squared, which looks like we're going to get 6e squared when we multiply all that out. Or sorry, 6e, not 6e squared, because obviously 1 squared there is just 1. So we get 6e. So we know now that this, if we pull this back up here, is going to be 6e. So real quick, before we sort of continue on here, let's just compare what we just did in this one versus the previous. Notice that in the previous one, when we were doing this error moment, this thing here was a strictly decreasing. So we used the lower end because since it was strictly decreasing, it was largest at the low end of the interval. Here, though, the second derivative was strictly increasing, so we chose the high end of the interval, the right endpoint of the interval, because that would guarantee that k was going to be as large as possible. Okay, now that we have all that, we can go back and plug this in. So our k is 6e, 1 minus 0 cubed, over, and we had 12n squared, and that's supposed to be less than 0.01. If you want to then, you could bring the 12n squared over onto the other side. So we would get, and of course the 1 minus 0 cubed is just going to be 1. So we get, this implies 6e is less than 0.12n squared. Then you could divide by the 0.12. And so this would imply that 6e over 0.12 is less than n squared. And then we could square root both sides. So this would tell us that the square root of 6e over 0.12 is supposed to be less than n. Now, that, of course, is the exact sort of value there, but we could come up with a sort of decimal approximation. So if we do that, square root 6 times e divided by 0.12, we will see that this comes out and tells us that we would need 11.66 to be less than n. So what was our actual end goal here? Well, we were trying to choose the minimum number of partitions. Remember, partitions is how many pieces are you going to cut it up into. So the number of pieces you cut it up into obviously has to be a whole number. So if we want the minimum thing, we need to pick the whole number that is greater than 11.66, that is as small as possible. So that tells us n equals 12. So we need at least 12 partitions to guarantee accuracy of 0.01 using the trapezoidal rule. So there we go. So as long as we use at least 12 partitions, 12 or more, then the error is guaranteed to be less than 0.01. Now, if we use fewer than 12 partitions, maybe we get lucky and the error is less than 0.01 because we don't know. But what we're saying here is that if we use 12 or more partitions, we guarantee that the error or the accuracy is within 0.01 of the true value. All right, let's quickly repeat this for the midpoint rule. So we'll move on to one more page here. So same idea for doing this for the midpoint rule. It actually should be very similar. The maximum error for the midpoint row is less than or equal to k b minus a cubed over 24n squared. And again, we want that to be smaller than 0.01. And so once again, we're going to focus on this component here. So we're going to pull this over to here. We're going to say that we want to solve k b minus a cubed over 24n squared less than 0.01. That means we're going to need to know the a, b, and k. Obviously, a is 0 and b is 1. And k, well, the k is the same for these because it's that upper bound on the absolute value of the second derivative. So that k is still going to remain 6e here. So we can put 6e. Plug that stuff in, and it looks like we get 6e, 1 minus 0 cubed, over 24n squared is supposed to be less than 0.01. Then we can solve this in a very sort of similar manner. We can bring the 24n squared over, and we get 6e is supposed to be less than 0.24n squared. Then this tells us that 6e over 0.24 is less than n squared, which tells us that the square root of 6e over 0.24 is supposed to be less than n. And of course, coming up with an approximation there, square root 6 times e divided by 0.24. That should come out as about 8.24 is less than n. So we need to make sure that n is a whole number that is larger than 0.824, but is as small as possible. Notice that tells us n equals 9. So we need at least 9 partitions to guarantee accuracy of 0.01 with midpoint rule. So notice that midpoint rule, because it has that 24n squared in the denominator as opposed to 12n squared, you can use fewer partitions to guarantee the same level of accuracy. So you would need fewer computations to guarantee the accuracy to within 0.01. Again, if you did choose 9 or 10 or 11 partitions, the accuracy might be much better than 0.01. Maybe it's 0.005 or something, but it's guaranteed to be at least 0.01. In our next video, we'll wrap up section 7.7 by talking about one more approximation, which is the sort of most accurate but also most complicated approximation. It's called Simpson's rule. Not only will we introduce how to run that approximation, but we'll also go ahead and learn how to estimate its error bounds.